An analog or analog signal is any continuous signal for which the time-varying feature of the signal is a representation of some other time-varying quantity, i.e., analogous to another time-varying signal. For example, in an analog audio signal, the instantaneous voltage of the signal varies continuously with the pressure of the sound waves. It differs from a digital signal, in which the continuous quantity is a representation of a sequence of discrete values which can only take on one of a finite number of values. The term analog signal usually refers to electrical signals. However, mechanical, pneumatic, hydraulic, human speech, and other systems may also convey or be considered analog signals. An analog signal uses some property of the medium to convey the signal's information. For example, an aneroid barometer uses rotary position as the signal to convey pressure information. In an electrical signal, the voltage, current, or frequency of the signal may be varied to represent the information. Any information may be conveyed by an analog signal. Often such a signal is a measured response to changes in physical phenomena, such as sound, light, temperature, position, or pressure. The physical variable is converted to an analog signal by a transducer. For example, in sound recording, fluctuations in air pressure strike the diaphragm of a microphone, which induces corresponding fluctuations in the current produced by a coil in an electromagnetic microphone, or the voltage produced by a condenser microphone. The voltage or the current is said to be an analog of the sound. An analog signal has a theoretically infinite resolution. In practice, an analog signal is subject to electronic noise and distortion introduced by communication channels and signal processing operations, which can progressively degrade the signal-to-noise ratio. In contrast, digital signals have a finite resolution. Converting an analog signal to digital form introduces a constant low-level noise called quantization noise into the signal, which determines the noise floor. But once in digital form, the signal can in general be processed or transmitted without introducing additional noise or distortion. Therefore, as analog signal processing systems become more complex, they may ultimately degrade signal resolution to such an extent that their performance is surpassed by digital systems. This explains the widespread use of digital signals in preference to analog in modern technology. In analog systems, it is difficult to detect when such degradation occurs. However, in digital systems, degradation can not only be detected but corrected as well. Advantages and disadvantages. The primary disadvantage of analog signals is that any system has noise, i.e., random unwanted variation, as the signal is copied and recopied, or transmitted over long distances, or electronically processed. The unavoidable noise introduced by each step in the signal path is additive, progressively degrading the signal-to-noise ratio, until in extreme cases the signal can be overwhelmed. This is called generation loss. Noise can show up as hiss and intermodulation distortion in audio signals, or snow in video signals. This degradation is impossible to recover, since there is no sure way to distinguish the noise from the signal. Amplifying the signal to recover attenuated parts of the signal amplifies the noise as well. Digital signals can be transmitted, stored and processed without introducing noise, even if the resolution of an analog signal is higher than a comparable digital signal. After enough processing, the analog signal-to-noise ratio will be lower. However, unlimited processing capacity to refine a digital signal and the resources required should not be taken for granted. In other words, processing capacity available for a digital signal is itself an analog signal. It reflects non-discrete factors in the real world, such as quantity and quality of computers, connections between them, sufficient electric power, shutdowns, hacker attacks, running costs, and everything else that can affect performance and availability. In comparison, analog signals are normally affected by a limited range of factors, whose degrading effect is, for the most part, already represented by the noise. So while an aircraft's altimeter may be thrown off if the plane suddenly enters an air zone with different pressure, it will give correct altitude most of the time. Subtle pressure changes are already covered by the small random vacillations an altimeter can be configured to ignore, in the simplest case, the trembling of the gauge arrow. Because a digital signal by definition does not vary with another continuous quantity that could be compensated for, all digital interference that does occur is to some extent unpredictable. Electrically, analog noise can be diminished by shielding, good connections and several cable types such as coaxial or twisted pair modulation. Another method of conveying an analog signal is to use modulation. In this, some base signal has one of its properties modulated. Amplitude modulation involves altering the amplitude of a sinusoidal voltage waveform by the source information. Frequency modulation changes the frequency. Other techniques, such as changing the phase of the base signal, also work. Analog circuits do not involve quantization of information into digital format, the concept being measured over the circuit, whether sound, light, pressure, temperature, or an exceeded limit, remains from end to end. Sources. Parts of an earlier version of this article were originally taken from Federal Standard 1037C in support of MIL STD 188.